Hello. In this video, we're going to continue with the idea of looking at regression, but a different technology is going to help. So here's what I mean. Take this data and let's plot the best fit power trend line to it. If we try to use Excel, I can right click on a dot, add a trend line, go to power, take a look at the equation in the R squared value, and notice we get a great value, 0.9941, and a reasonably good fit. And so we can see how that works out. So 4.6505 times our x value raised to the 0.6063 power. And so there's our data points. If we wanted to compare that and make sure that we type the model in correctly, we can do another chart. And sure enough, this plot of the points looks like our line. So we have the appropriate parameters for our model. If I want to calculate SSE, remember I just take the difference in the model and the actual and square it. Drag that down, and then add it up. And so we get an SSE of 1,935. And that's the minimum possible SSE for the transformed data. But as we've said, that doesn't necessarily mean that we found the best model for the original data. And so the interesting thing is that we might have better success finding that actual ideal model, or at least a better one, not with a spreadsheet, but with an old technology, and that's log-log paper. So let's take a look at that. So log-log graph paper comes from the idea that if I want to model a power function, something of the form y equals a times x to the b, then I need to take the logarithm on both sides. And in this case, I'm going to use the base 10 log as opposed to the natural log. So the common log of y equals the common log of ax to the b. And so we get as log of y equals the log of a plus the log of x to the b, or what's the same thing, the log of a plus b times the log of x. And so if we let capital Y equal log of y and capital X equal the log of x, then notice our new equation is capital Y equals bx plus log of a. And so now we have a linear equation. And so the idea is that if I can somehow plot not x versus y, but log of x versus log of y, if the relationship is truly a power function, then that transform plot should be linear. And we've seen this in chapter 2. That was the whole basis for how Excel finds the best fit trend line. So let's see how that works on graph paper. So here's an example of log-log graph paper. So this paper is designed in a way to do those logarithms for us. And because it's going from 1 to 10, and then 10 to 10, 10 to 10, and the lines are not equally spaced, we can see that that is a logarithmic scale on the x-axis, and since it's doing the same thing on the y-axis, it's also a logarithmic scale there. And the reason why the lines aren't equally spaced is because if you think about the logarithm of certain numbers aren't equally spaced either. For instance, what's the log of 9 is about 0.954, and the log of 8 is about 0.903, versus the log of 3 is about 0.477, and the log of 2 is about 0.301. So notice there's a larger gap between the logarithm of 2 and 3 versus the logarithm of 8 and 9, even though they're just one unit apart from each other. And so that's why we see here that the gap between 2 and 3 is more than the gap between 8 and 9. And so that exact relationship is shown in this scale. The other thing we need to know about logarithmic graph paper is that the scale has to be adapted to our needs. So for example, if this represents 1, then this represents 10, then this represents 100. So it helps to actually write what the values for each axis is. And then that means that a number like this 4 represents 40. And this 10 over here would represent 1,000. And this paper is flexible enough that if I wanted a different scale, for instance, if I wanted the scale to start at 100, then this would be 1,000, this would be 10,000, and so forth. And then this number, this 4, would actually represent 4,000. So depending on where your data lives will determine what the scale of your x-axis and y-axis will be. So for example, if I wanted to plot the point 35, comma 0.6, 35 would be over here. Let's say I'm using the blue scale, okay, and I want 35. So this number right here is 35. And then 0.6, well, notice if I want 0.6 on my y-axis, then I really need this to represent 0.1, and then this y value would represent 1, and this y value would represent 10. So 35.6 then, so this would actually represent 0.6. And so that point right there, whoops, I'm off one. That point right there would be 35, comma 0.6. And as you can see, it's easy to make a mistake because the lines are close together at certain points. So you have to be careful, but that is how logarithmic graph paper works. Notice that because of our scale here, we've got 10, 1, 0.1. If I went another cycle down, I would not be at a negative number, I would be at 0.01. And then the next cycle would be 0.001. So as you go to the right, you're always increasing towards infinity. But as you go to the left, you're always decreasing down to 0, but never actually reaching 0. So there is no 0 axis. But if you think about what the log of 1 is 0, and so basically when I'm trying to find an intercept here in a moment, I'm going to use the fact that the log of 1 is 0, so the 1 axis is going to play the role of the 0 axis in a traditional graphing problem. So those are a few things to be aware of log-log paper. And remember, we're going to use this to find an optimal power function, and the more linear the data is when we graph it, the more likely we'll have a good power function to fit the data. So this is the basics. Let's jump into an example, and we'll do that in our next video.